Can you see the screen, everyone?
Yes.
So kind of wearing two hats today, as CIBSE committee member and as the presentee for Mixergy. Just want to welcome everyone to taking out the time out of the day to be able to join us. The CPD is going to be covering adaptive heating technologies and their role in decarbonisation of heat. My colleague David White will be able to answer any technical questions as we go in the chat box. If you would like a PDF copy of the presentation and a CPD certificate, if you could pop your email address in the chat box, and just for us as a regional committee, because we're interested in where you guys are actually from within the region, if you could just put where you're from. If we've got international great people from further borders of Yorkshire, we're also happy to hear from you where you're from, just to see where the wider audience is. So what we'll do is we'll get started. So the contents of this CPD is not meant to be overly technical, but more aimed at providing an introduction to the challenges of decarbonising hot water in buildings and the role that low carbon technologies can potentially play. So carbon emissions play a major role in climate change. Limiting emissions of greenhouse gases, and carbon in particular, will have a major impact on the mitigation of the climate change and limiting global average temperature rise. The 2016 Paris Agreement within the United Nations Framework Convention on Climate Change was signed by 195 nations. The agreement's long-term goal is to keep the increase in global average temperature to well below 2 degrees C above pre-industrial levels, and to pursue efforts to limit the increase to 1.5 degrees C, recognising that this would substantially reduce the risks and impacts of climate change. As part of Theresa May's exit from the Office of Prime Minister, and as a legacy, the Climate Change Act 2008 was amended to set an ambitious target of net zero emissions by 2050. The UK was the first major economy to enshrine a net zero carbon target in law, and the Climate Change Act commits the UK government by law to reducing greenhouse gas emissions by at least 100% of 1990 levels, deemed as net zero, by 2050. And this includes reducing emissions from devolved administrations of Scotland, Wales, Northern Ireland, which they currently account for around about 20% of the UK's emissions. Although Boris Johnson announced in April this year that a 78% reduction in carbon emissions by 2035, which is a big step up from the UK in its carbon reduction policy. Since early 2019, over 270 local authorities, including regional, district, town and parish councils, plus UK government themselves, have all declared climate change emergencies. Many of these bodies are looking at fast-tracking carbon emissions reduction targets and aim to become net zero by 2030 in the earliest cases. The practicality of these declarations and bringing forward these targets are not fully understood by the authorities, which is where we can help to provide support and solutions. And whether you agree with their methods, organisations such as Extinction Rebellion, quite recently in the news we've seen Insulate Britain, certainly raising awareness, whether you agree with their actions or not, but certainly starting to now make an awareness of climate change. So the UK's ambitious net zero carbon emissions target by 2050 and the 78% carbon reduction emissions by 2035. In 2018, the UK were 44% below 1990 levels, according to the Committee on Climate Change. The UK's first carbon budget between 2008 and 12 and the second between 2013 and 17 have all been met, and the UK is actually on track to meet its third carbon budget between 2018 and 22. However, we're not on track to meet the fourth carbon budget, which covers a period of 2023 to 27, and further drastic action is needed across all sectors to meet future carbon budgets and the UK's 2050 target to reduce emissions by at least 100% of 1990 levels. And it will require reducing domestic emissions by a further 3% of 2018 levels. So in reality, this is 50% higher than under the UK's previous 2050 target and 30% higher than achieved on average since 1990. So a massive step up in action is needed to achieve these levels. In turn, this is driving behaviours in the building regulations and SAP as we move towards SAP 10.3 and SAP 2025. Local authorities have access to decarbonisation funds, which targets EPC scores to be a B by 2040. Gas boilers are being phased out of new builds and utilisation of heat pumps and infrared technologies. And as we start to move to things like Part Z in the building in London, and which will be later adopted by the rest of the UK, manufacturers have been required to start to locally produce their components, so embodied carbon is taking its part. So let's address the challenges of decarbonising heat. Decarbonisation of heat in homes presents one of the greatest energy challenges in this critical decade. An urgent move to phase out fossil fuels and manage a greater renewable energy capacity coming online. Protect households from fuel poverty whilst providing comfort and better control. The balance between cost-effective standards of new homes and offering solutions for existing homes. There are currently around 126,000 gas-safe registered installers in the UK, and we need to grow and retrain the installer base to deploy the new technologies and address grid constraints due to electric vehicle and the electrification of heat. So, if we look at network constraints, the UK power infrastructure is like the veins of the country, pumping power around England, Scotland and Wales. The power lines can only take so much energy, and the more wind power, solar power we add to this, the more uncontrollable those supplies we have connected. Linked to the reduction of gas, which is what we call as a flexible load, more inflexible and unpredictable renewable energy coming in has created a difficulty to manage electricity network that can often be overloaded with unused energy. As we look to our energy production, we have increased the amount of inflexible energy from wind and solar and reduced our flexible options. We are closing down our coal power stations and reducing natural gas use, and we'll end up with a 50-50 mix by 2040 with an increased requirement for storage and control technologies. And there's a fantastic little carbon app which you can download which tells you exactly how much power is being generated in the UK today and what currently the proportion is, and that app is called Grid Carbon. So currently at the moment, from when I last checked this morning, we're producing around about 10,700 megawatts of energy from wind, which is around about 31% of our power, which is actually more wind power today during this period today than gas, which is normally around about 10,300. And it's interesting to see how much it changes. But the mix of energy production is influencing the decisions made about which technologies we should be using for heat and cooling. We increase the production of renewable energy, so that through whether that be solar or wind, we end up reducing the carbon intensity of that electricity. So if we go back to 2018, the carbon intensity of electricity was over 300 grams of CO2 per kilowatt hour. And as we bring in more renewable technology into the carbon intensity is reducing, and it's forecast by 2030 we'll have cut the carbon intensity down by half to 150 grams of CO2 per kilowatt hour. This has been recognised within our building regulations, for example with heat pumps, because if we get a COP of a 3 from a heat pump, we can then reduce the carbon intensity by a third, and as a result it allows us to use technology which is a lower carbon intensity of gas, which is fixed at 250 grams of CO2 per kilowatt hour. We are now seeing a rise in assets that utilise electricity as the carbon intensity is falling and it's becoming a better solution for our planet. But it makes balancing the grid more important. The balancing of the grid is reflected in the wholesale market of prices of electricity. Every day is split into 48 individual pricing points of energy, and energy providers bid on each block of amount of electricity they need to service the needs of their customers. So, for example, every 30 minutes, the customer may need, say, we just had 10,300 megawatts of energy. The next half hour may be 15,000 megawatts of energy. The more demand for the energy in that 30-minute period, the higher the price will be. The lower the demand, the lower the price will be. We then have the half-hour settlement of the market. The energy companies bid for the electricity and set the price, and then set as at a fixed rate, and then they add their tariffs to pass on to the customer through a markup. We're seeing more and more renewable energy pumped onto the grid. The lower cost of electricity becomes, the more off-peak energy used, the lower the price becomes. And becoming quite often, electricity is dipping below the price of gas, which gives us an opportunity for off-peak energy storage. Although over the last few weeks we're currently in the energy crisis, as we're starting to have gas, amount of gas which should have been stored for the winter, a lot of European countries and the UK itself has reduced the amount of storage of gas, which is now put us kind of liable to price fluctuations. We're now seeing gas is going up by 350%, electricity by 250%. But let's have a look more at negative pricing events. As more off-peak electricity is coming into the grid, there is a problem now managing the frequency. The more power that goes down those electricity veins, the higher the frequency becomes. National Grid is contracted to keep 50 Hz with a tolerance of a Hertz. As more power is being pushed into the grid from renewable sources, There is an abundance of power that must be used and it creates a negative pricing event. This means customers will be paid to use electricity. This is where there's an opportunity for thermal battery storage. But before we talk about different types of electrical energy storage, just want to touch on fuel poverty. Who are the fuel poor? So you can get a copy of this presentation by PDF if you want to put your email address in the chat, but just pick up a few highlights. Fuel poverty is a term that is bandied around the UK, and it's assumed that the fuel poor are the elderly, unemployed, who are most affected. It surprises most people that fuel poverty has a far wider reach on society. 49% of people in fuel poverty are in work, and 30% are more likely to be couples with children. Another misconception is that it is linked to fuel poverty is linked to property energy efficiency ratings and people in the third and fourth tier income too. 13% of people in the third and fourth tier incomes are actually in fuel poverty, and 60% of them are likely to live in a home with an E, an F or a G energy efficiency rating, and 56% are who live in the properties that have been built before 1944, so they have poor thermal fabric, no cavity walls. So let's look at a few options on how we can actually store energy. The first option is a battery. You may have heard of the Tesla Powerwall, Powervault, but there are lots of different home batteries being installed currently today. They're brilliant at storing electricity, whether taken from a cheaper tariff or local generation from PV. The challenge is they have a massive capex to buy and install. In order to pay for themselves, the return on your investment is typically around 10 years, but limitations in the battery is the amount of charge cycles. You'll know them from mobile phone ownership. The more you charge it over the years, the less battery time is available, and you end up charging it more often, becoming a vicious cycle. If you look at a 10-year payback, and charge cycles are high, in theory, the battery could die before the end of that payback period. There's a very high material intensity, typically more than 100 kilograms of copper, lithium, cobalt, but it could become scarce as electric vehicle production ramps up and increase the cost. Batteries provide no other service to the home other than storage and electricity, and things like lithium fires can be difficult to extinguish, but it's a technology that is being utilised. But what we tend to find, the return on investment, you tend to break even by the end of its life, rather than actually starting to put a high energy saving and a cost saving to the property. So store energy in a traditional hot water cylinder. Traditional hot water cylinders have been used in many different ways since the early 1800s. First unvented cylinder was developed by Sir Thomas Hawksley in 1861, and the design has relatively stayed stable since then. Today, a traditional cylinder comes in three forms: direct, indirect, which are open or unvented; direct, which utilise electric immersion heater; indirect, with a coil at the bottom of the cylinder, which usually has a boiler as a heat source, which is then water's fed from a heat tank, usually located in a loft space. A direct tends to be more unvented, pressurised. Which is unvented, this can be direct or indirect, but they're a sealed system that uses high water pressure to deliver hot water faster. By being a sealed system, the water is able to heat faster than a traditional open-vented cylinder. We then have some more specialist types of cylinders for heat pumps, solar thermal, which have larger coils to transfer the lower grade heat to usable hot water. These tanks are much larger due to the size of the coils and can be harder to install in traditional 600 by 600 airing cupboards, so it can be difficult for retrofit practices. Water is heated from the bottom. The whole tank has to be heated to create usable hot water or to pasteurise for Legionella. Water is great at convecting. Lots of hot water is created above the heat source, but the water is a poor conductor, where we're left with a grey area of water below the heat source, which never reaches pasteurisation temperature, which creates a problem for water hygiene policies. But if we've taken a low amount of electricity, so we're only putting 500-600 watts, if we look at the top left-hand graphic where my cursor is, we're only going to heat a little bit of water. It's not going to be stored as usable water. So storing usable energy into hot water in a traditional cylinder has quite a few drawbacks, unless you have an abundance of power. So what other technologies can we look? This is where we can look at thermal batteries. Whilst there's a huge market push on electrical storage batteries, heat batteries are now starting to prove their worth. The principles of PCM storage, or phase change material, has been understood for many years, but only recently has a safe and practical heat battery been launched. Heat has traditionally been stored in water. This has been very successful due to the natural high specific heat capacity of water. So water can store around about 10 times as much heat as the equivalent mass of copper. However, despite its efficiency, where relatively little space is available, the materials that can be used to store over 4 times as much heat as water at the same volume. How does phase change material or PCMs work? For this CPD, we're going to concentrate on heat rather than cooling. PCMs can be heated from a variety of sources, from a boiler, heat pump, solar, or even district heating. Traditionally, heat is stored in water by gradually adding energy until it achieves a safe maximum temperature, usually at 75 degrees if a blending valve can be used, and at this point it's no longer possible to store any more energy. PCMs are solid at room temperature, and it takes energy to melt them at varying temperatures, usually in excess of 58 degrees C. Typically, there could be around about 4 times as much energy stored in the water at the same volume. Energy can be added in following ways: solar thermal energy via a liquid flowing through a heat exchanger, most efficient; electrically generated from solar PV during the day, cheap off-peak electricity, or from a heat source like a boiler, a heat pump. Heat can then be extracted as hot water to outlets or as space heating via radiators and underfloor heating system. But the pros and cons of PCM materials are still being debated. Few pros are: the PCM can store 4 times as much energy, which gives a smaller footprint, has a maximum temperature of 75 degrees, so we can store a boost in usable hot water if it's blended down to a tapping temperature of 40 degrees C. Some of the cons: PCM materials is more expensive than traditional hot water, and it's a lot heavier and weight can be a factor during a build and retrofit locations. The lifespan of a PCM is still to be proven over a longer period of time. There's lots of estimates, but we've seen hot water generation a traditional way for just over nearly 200 years. But if we look at the lifespan, it's still to be seen. But we also have to look at the impact of PCM materials on recyclability. Yes, some can go to landfill, but how does that affect future legislation when it comes to embodied carbon? What other options are there? We can actually use a domestic hot water cylinder as a thermal battery. And this can be used with lots of different energy sources, whether it's direct electric, it could be a coil with a gas, oil, or in future hydrogen boiler, it could be with a heat pump, or it could be with solar PV. But to achieve this, traditional hot water systems has had to be redesigned so that we can store hot water in 1% increments. The heat source is located at the top of the tank, and depending on the heat source used, the initial charge of hot water would be between 10 and 15%. As the temperature sensor recognises that the tank is charged to between 10 and 15%, it will then start to take water from the bottom of the cylinder through a variable speed pump, atomise it into the top. So imagine like a cup of hot tea. If you pour cold water in, it cools it. If we atomise cold water into hot, it equalises temperature, and we're able to store that energy and get the cylinder to stratify and keep the water what we call crisp. So what we want to do is keep the water, go back a slide, the water above, if we imagine that disc as like a thick piece of rubber, it's actually made from water. If we keep the water above 50 degrees at the top, 18 degrees at the bottom, we're able to control that as a usable battery and store heat. So every watt of energy that goes into that tank is usable heat. So let's talk a little bit about the pros and cons. Energy stored as usable hot water. It's future-proof as it can take 4 heat sources along its lifetime, and we get 30% more usable hot water due to 100% of the cylinder being heated and pasteurised. So where we talked on these couple of slides back that 30% of the tank isn't actually heated or usable water, because you're able to stratify the tank and control that thermocline disc, we can actually push it to the very bottom. There's a benefit in SAP from new build in Appendix Q and also in retrofit in RD SAP. But some of the cons is it has an increased cost compared to a traditional cylinder, as it has extra technology, machine learning and brain on it. So how can we use machine learning to reduce our carbon footprint? We can also see that people use a lot less hot water than we think. So we use one of the experiments we carried out at Mixergy. First of all, with 100 tanks, we wanted to work out the probability of someone using 100% of their tank in one go. What we actually found is less than 5% probability of someone using 50% of their tank in one go. So where we're currently sizing cylinders with a heat pump at 35 litres per person, or some people with a gas boiler will still be sizing at 45 litres per person, we're sizing hot water on a one chance that the hot water could be overloaded. Everyone in the household was taking water once after each other. We've got visitors, And what we're doing throughout the year is storing excess energy in water which isn't being used and lost in standing losses. So this is some real-time data. We've actually moved up to now, we can show this over 900 odd cylinders, so I need to update this slide, but we're looking at this series of tanks, 571 tanks. What is the probability of them being able to use 100% of the tank? So we can see peak usage is at 6:50 AM, which is a maximum charge capacity of 54.6. So those 571 customers with a thermal battery storage cylinder would have wasted just over 40% of their heat in standing losses. So we can start to challenge the norm and start to store energy, less energy in water to usable heat, but it also gives us the ability to then utilise energy storage from things like PV or cheap electricity tariffs. And this is where machine learning can take in. So now that we can touch on the Appendix Q side of the benefits of the Mixergy cylinder with solar energy, a regular cylinder, which is demonstrated on the left, has to be heated to full every day, otherwise the home will not have usable hot water for the morning period. If we look at hot water usage at 6 AM, we've actually depleted the tank by 42%, and that's the rest of that is lost in standing losses. It's a waste of water, and we've only got 42% of the tank that can be topped up locally from generated PV. Using machine learning and reducing the actual amount of hot water created to match need, this Mixergy tank has been able to be charged at 20% for 6 AM. We've had a drop in hot water usage in the morning, but 88% of the tank was able to be recharged from locally generated PV. What we can do is show you this a little bit more in a heat graph. So what I'm not going to talk about at the very top, you can see as you get to the colours which are warmer in summer months, it gets cooler in winter. But this tank, using machine learning, is biased to not create any hot water other than solar PV during the day until 5:15 in the evening, and then it will kick in and create 20% with the gas boiler if it hasn't been able to achieve that target during the day. So for 10 months of the year, between January and October, we were able to create between 30 and 80% of hot water from locally generated PV. The gas boilers had to kick in at a period of times for top up, or if it's not been able to make enough during that solar gain. And as we move to November and December, that's where we had a couple of decent days of solar, but that's where the machine learning has kicked in the boiler to be able to take over. So what we've been able to do is offset the primary energy and reduction in carbon for 10 months of the year, which can prove a significant saving when it comes to Appendix Q and RDSAP. So I want to talk a little bit more about what else can machine learning do. So what we're able to do with machine learning is we can see things like if suddenly there's a high heat up period or a quick rapid depletion of hot water, it could be that there's an external leak. If it's above a head, you'll notice it. If it's under a concrete floor or if it's in a plant room, the cylinder is able to use machine learning to monitor its surroundings to say, we think there's a water leak, and notify the asset manager. In local authority world, it's able to do welfare checks with machine learning. So if you've got a vulnerable tenant who's created, it could be an elderly tenant, created hot water every day for 2 weeks, but hasn't drawn a single litre of water, the cylinder is able to, through the machine learning, to recognise that there's no hot water, and it can create a welfare check for the asset manager to say, this is could be a vulnerable tenant that could have gone on holiday. What also it can do is pick up things like inefficiency. So pick on tank 102, this is live data from earlier this year. So when hot water is generated, we should have a nice, steady, sharp rise. If what we call the jaggies, so the cylinder coil is going hot, cooler, hot, cooler, hot, cooler. This is telling us that the gas boiler is actually starting to is turning on and off and cycling. So a couple of things what machine learning can do to save energy. This has been verified by the Energy Savings Trust. We're able to save 21% in gas consumption. So what the cylinder is able to do is look at the flow temperature and artificially keep the coil cooler. So that atomizer we showed in a few slides back, where if we equalize temperature, if we increase the speed of the variable speed pump, the cylinder is able to keep that coil cooler within 5 degrees cooler than the boiler primary flow temperature, so they can move up to temperature together, and then it can start to reduce the amount of flow of cold water to be able to then let the cylinder water achieve its set point temperature. If that's been enabled, the machine learning is then able to identify if the actual heat source has got a problem. So if its boiler is still cycling after that method has been employed, it shows it could be a problem with the heat source, whether it could be a partial blockage in the main heat exchanger, could be an NTC temperature fault, or it could be a weak pump. But it's able to report back to the asset manager or homeowner to say, we've got an energy efficiency problem with the heat source. So machine learning can access dynamically priced tariffs. The most recognised time and use tariff is Octopus Agile. That links into the customer's electricity prices and links back to wholesale pricing. They get 48 set price points every day issued to them at 4 p.m. on an evening, which then can be used to make it flexible hot water and take advantage in off-peak energy. But unless you have assets what easy control, and you'd have to physically turn on a dishwasher or your washing machine. But using machine learning, they can actually access those tariffs and download. Apologies, my laptop seems to be bouncing around today. So let's look at some live data from November 2020 last year. What this tank was at 2 a.m, it was 30% full of hot water. We had 2 negative price points on that evening. So the immersion heaters turned on for an hour, turned off, on, off, on. So between 2 a.m. and 5 a.m, we was able to utilise from 30 to just over 90% of hot water for free. So effectively a free tank of hot water. And that customer was paid to use 5.3 kilowatt hours of electricity. So one of the things you'd think is, well, if I've got a heat pump, we could utilise that free half hour. But in a half hour period, so let's look at, say, between those 2 periods of half hours, by the time the heat pump is actually ramped on and started to heat water, it'd have had to been switched off again for the next negative tariff. So this is where we can start to use machine learning to actually choose where is best to put that heat source. And during those half hour periods, unless we've got a long period, it's cheaper to use the immersion heater rather than something like a heat pump. Thermal batteries can also be used to utilise firm frequency response and demand side response. As we move towards more renewable electricity generation from wind and solar PV, excess electricity on the grid can become dangerous. And as growth of renewable energy systems in the UK has led to some interesting challenges, in the northwest of Scotland, wind farm operators on occasion are paid up to an excess of £1 million a day to shut down when there is too much wind. Meanwhile, in Cornwall, there's a memorandum that PV installations in some areas due to excess power in summer months. A thermal battery, linked up to thousands of others through connectivity and machine learning, can be used to offer fixed firm response and DSR services. So within 100 million a second, National Grid can talk to the smart cylinders to ascertain how much hot water, how much cold levels, and a computer algorithm can offer capacity to take an excess electricity. So for example, within 100 million a second, the tanks can join up and take 1.5 megawatts of capacity. All the immersion heaters switch on to balance the load on the grid, and there's a benefit to the customer can be taken in 2 ways. If the customer can be paid to heat the hot water and on an agile tariff, or through machine learning for non-agile electricity tariff customers, the electricity used and the hot water created during the DSR event can be offset against their normal schedule so that the offsetting cost and reduce their carbon footprint. So in net, it doesn't cost them anything. What we're able to do is actually get more capacity out of the grid and take advantage of that renewable energy. Because then, if you remember, every watt of energy what's stored in a thermal battery is usable heat. And finally, in conclusion, before we talk a little bit about some case studies, the UK is still at an early stages of our journey towards becoming net zero, and the increased demand of our electricity network from the electrification of heat and electric vehicles need to be managed in a cost-effective way. We're increasing the amount of inflexible electricity, and today the UK produces around 26% of electricity from wind, and by the end of this decade will increase to 76%, and DSR and FFR instances will become more frequent. No technology will be a silver bullet to solve our problems, but using a mix of batteries, PCM, and thermal batteries to store excess energy will have an impact on the reducing the cost and increasing of our electrical infrastructure, and coupled with machine learning to tackle fuel poverty by reducing energy consumption and storing cheaper/free electricity to usable heat. Finally, just want to talk about a couple of case studies. This one's with Ocean Housing. What they wanted to do is create hot water for their tenants at a lower carbon footprint than a gas combi boiler. So if we look at a gas combi boiler, will create hot water at 230 grams of CO2 per kilowatt hour, where a Mixergy smart cylinder can create it at 183 grams. So what we did, we installed 71 Mixergy tanks, smart cylinders, and if you look at the plum-coloured graph, this is where the tenants set their hot water schedule using an app. This is where they thought they needed hot water. We monitored it for a period of time and then turned on the machine learning. Machine learning skewed the hot water generation between 3 and 6 a.m. So we were able to create more hot water in the morning during lower electricity tariffs. And during the day, they actually used, in most cases, more than half of what they needed until we got to about 9 o'clock when it caught up. But some of the benefits were, compared to a normal direct electric tank, we was able to reduce our energy costs by 35%, so between 125 to £80 a year, which is a large amount if you're in fuel poverty. By creating the hot water in the morning between 3 AM and 6 AM, we was able to utilise more wind and nuclear power, so we reduce our carbon emissions by 16%. And by moving from the customer's tariff schedule based on the app to machine learning, the machine learning was able to actually save them a further 12% in energy costs. We've got a few projects where these are being utilised, from South Wales, Calla Homes in Scotland, and a brilliant project in Nottingham, which was done using Energy Sprong, which you can, if you want to find out a little bit more of those, get in touch. And finally, thank you very much for listening. If you'd like a PDF copy and a certificate, if you could please pop your email address and where you hail from, just so we as a committee member can see how far and wide our region's reaching. And thank you very much. And we'll check the chat and see if David's got any questions.
Thanks, Tom. You clearly did a good job there because no questions have come in.
Okay. This is where we know who's having a shout, who's having a sandwich, who's walking the dog. So we've got someone from Northern Ireland. Okay. We do have if anyone would like to book, we do have an extended technical presentation which covers the technology, because we've had to do kind of an overview of different technologies. So we can talk a little bit more about the Mixergy. What I'll do is pop my email address in the chat box, and if you'd like to know further, just get in touch and we can arrange some technical presentations over Teams, which tend to be, we are starting to open up now. We can actually bring you down to our facilities, or we can come visit you. In the whole of 2021, I've only been able to present in one person's boardroom, so I am eager to get back out and get moving.
We did, one question's just come in, Tom, whether the cylinder is available for commercial deployment. So I guess the answer to that is that at the moment our off-the-shelf sizes go up to 500 litres, which is good for kind of small commercial applications. We have done projects up to 10,000 litres in size, but typically anything that sort of size is a custom design project, because there's all sorts of logistical issues about how you get the unit into the property. But yeah, so it does scale for commercial application, I'd say, is the answer to that question.
So we've got the capital costs. So on average, the uplift of, we can only talk about the Mixergy because we don't do the other technologies. We're on between 150 to £300 more than a traditional hot water cylinder. But if you're coupling it up with solar PV, it normally pays for itself. So it pays for the difference between the traditional and the Mixergy cylinder in about 2 years. If you're using it just as a standard efficiency saving, so in gas we reduce the efficiency by 21%, 35% in electric. It's now about 3 to 4 years to pay that difference. Overall, we expect it to pay for itself between 10 and 15 years. But we've designed this product to be in someone's home for between 25 and 30 years, because grid services is important to us, and we want to be able to provide those grid services over a longer period. Hope that answers your question, Mark. Copy. Just a few people copies of the presentation. Any further questions?
I believe there was a question about capital costs up the way there.
Yep, we've just talked about it's between 150 to £300 uplift to a traditional hot water cylinder. So if someone who specifies megaflow, for example, you have probably around about £150 difference. If you specify something much cheaper, it's normally the £300.
Yeah, I would say the most common sort of price point for the product is probably about £900. If you were to average every cylinder sold over the last 12 months and then run an average, it'd be about there. The price increases if you add on extra functionality, such as like an embedded solar PV diverter or the heat pump kit, and the price would go up. And then if you're just using it as a standalone direct electric cylinder, price comes down. So it does vary.
I'll let you answer this one, David. This is your background.
Okay, what sort of BMS controls are required to apply your analysis system to an existing project? So there are three ways in which you can control a Mixergy style system. So we have our onboard conventional controls, which are all managed, monitored, accessed through the cloud. And that means that if you were an asset manager and you had hundreds of assets connected, you'd use that as your primary controls interface. If you then wanted to connect your fleet of connected hot water tanks to a larger system, you would then have an API. So the API is some code which you can use to then communicate with various defined points within our control system. So you won't be able to access everything through the API, but there are certain data points which we make accessible through the cloud. We do have projects where we use an open protocol controller that can communicate via Modbus or BACnet. And one nice example of this is a project in South Wales called Park Erin, which is a development by Sarah Holmes, where they use communal ground source heat pump loops, each feeding a fixed number of properties. And those properties are controlled by a local building energy management system. So they would use the BMS to communicate with the tanks, and the tanks are slaves rather than masters. So we've got local control, which is hardwired into a BMS system, either BACnet or Modbus, or we have cloud controls connected via API. So those are the two predominant control options, as well as there are some local physical controls, but they have very limited functionality. There's one question about PV diverters. So Mixergy make their own PV diverter, which is currently most popular from new build market because it's pre-wired, pre-fitted. For the retrofit market, where people already have PV diverters, the tank will work with any PV diverter, whether that's a Solar iBoost or a Might Energy Eddy, are the two most common that our customers stick their cylinder alongside. But it's not fussy about what that PV diverter is.
Any more questions for anyone else? It's looking great attendance. I think peak I saw when I checked was 53, which is great for Yorkshire CPD. If there's no further questions, my email's in the chat box, and thank you everyone for attending.
Thanks all.
Thanks for your time today, Tom and David. Really appreciate